I'm Mark Rennies, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 31. In the United Kingdom, there are 8 denominations of coins in circulation. The 1 penny, 2 pence, 5 pence, 10 pence, 20 pence, 50 pence, 1 pound, and 2 pound coins. And a pound is simply 100 pence, so those last two coins are simply 100 pence and 200 pence, respectively. The problem asks us to count the number of ways to sum up to 2 pounds or 200 pence. Let's jump right in and write a draft for a naive solution in Lua. To start with, we define our list of valid coin denominations, from 1 up to 200 pence. Remember that Lua only has one composite type called a table, so we define dictionaries, lists, and objects using the same curly brace delimiters. Now we need a recursive function. As a starting point, we might try to write a recursive function that takes a single argument indicating the amount of money we need to sum up to. Under that assumption, if the amount of money left is less than 0, we've overshot our goal and there's no solution. Since we're interested in the count of solutions, the return value in that case is 0. Next, if the amount of money left is exactly 0, then we've found a single solution, so return 1. Otherwise, there's a positive amount of money left. So consider all of the coins we could add to our collection, and recursively call our function to sum all of the solutions from those smaller subproblems. Finally, return the sum. Outside of our function, we simply call our recursive summation function with an argument of 200 pence, and then wait several non-alien years for this program to run. See, the problem is, this is an exponential time algorithm, which means as we increase the input value by a constant amount, we multiply the amount of time needed to run our program by a constant. I ran this program with some smaller inputs to collect some data, and this is the graph. The x-axis is the magnitude of the input value, and the y-axis is the execution time. Using this exponential regression function, we can estimate that when the input value is 200 pence from the problem description, this program should take approximately 5.4 duodecillion seconds to run, or 174 non-alien years. Keep in mind that modern estimates say our universe is only 13 billion years old. Compared to that, 174 non-alien sounds like a positively made-up number. It takes a while to even see that number in Cookie Clicker. The good news is, if you decide to go brew a hot pot of coffee, add some creamer and sugar, and drink it very, very slowly over the lifespan of the universe, then at the end of 174 non-alien years, you'll be rewarded with an incorrect answer anyway. Unfortunately, we've massively overcounted our desired value. Our current program assumes that the collection of coins is ordered. In principle, I could get up to 2 pounds by having a 1 pound note plus 2 50 pence coins. Or I could do the same by having 2 50 pence coins and a 1 pound note. In both of these situations, I have the same coins, but I simply chose to tell you about them in a different order. Our current program counts these as separate solutions, even though the unordered set of coins is the same. For every intended solution to our Project Euler problem, our program will count every permutation of that solution separately, and that's not what we want. We don't want to count ordered sequences of coins. We want to count sets, or rather multisets, of coins where the order doesn't matter. Equivalently, we could simply demand that all of our solutions are in a particular canonical order. So from this point onward, I'm going to assert, without loss of generality, that the only valid solutions are those where the order of the coins is monotonically decreasing. That is, the 100-50-50 solution is valid, while the 50-50-100 solution is not, since it's in the wrong order. In this way, for each multiset of coins, we've chosen a unique ordering to represent that multiset in our solution. To implement this modification, we'll add a second parameter to our recursive function. As we build up our solution, that second parameter will track the most recent coin denomination used, which due to our decreasing order requirement is also guaranteed to be the smallest denomination we've used so far. From that point on, we're only allowed to use coins of an equal or smaller denomination. Inside of our main recursive case, we insert an additional check that the coin we're considering using right now is at most as large as the last coin we used. For our starting conditions, we still want to add up to 200 pence, and our starting denomination is the largest one we have, the 2 pound or 200 pence note. This gives us the flexibility to use any coin we want for our first call. This solution runs in a little under a second and gets us our answer. When we talk about our main language for this week, this is what we'll use as a guide. But in general, this solution is still suboptimal for larger inputs, and if you've seen any of my other videos on this channel, I think you already know why. This is a recursive function in 2 arguments. The first argument is bounded between 0 and 200, while the second argument must be the currency value of one of our 8 coins. That means that, in total, the number of distinct, interesting calls we could make is bounded above by 201 times 8, or 1608. But I can promise we make a lot more recursive calls than that. In fact, with a small modification to this program, we can actually count the number of recursive calls we make, and we find that it's 2,886,726 calls. I haven't explicitly checked it with a calculator, but I'm fairly sure that number is bigger than 1608. So as is prone to happen in this series, this program can benefit from caching. We've done caching tricks before in Lua, but as a brief reminder, Lua tables use strict object identity to identify keys. This means that even if we have two tables that look identical and have the same keys and values, they still count as distinct keys in a larger table. For example, note that the tables x1 and x2 are, for all intents and purposes, identical. They both have three values, 10, 20, and 30 in order. Yet if we store a value in the composite table at key x1 and then retrieve the value at x2, we get nil, the default value, since Lua's key equality function still considers these two tables distinct. This contrasts with Python, where the equivalent code using tuples as the keys would recognize the two tuples as the same. This also means that Lua, unlike JavaScript, considers numerical and string keys distinct. With all of that in mind, we want the keys for our cache table to consist of the amount of money left and the last coin we used. To do that, we'll construct a string with the two values separated by commas. Once we have our cache key, check if it's in the cache, and if so, return the stored value. Note that in Lua, like in Ruby, only the values false and nil are falsy. So even if the value 0 appears in our cache table, it will still count as truthy for this conditional. If it's not in our cache table, do the usual summation, but store the result in the cache for later use. This version runs in, well, fast enough that I can't really measure it easily. This is a pretty neat caching solution, but just for fun, we can also do the entire computation in reverse. Our recursive calls have a clear direction to them. The money left argument is getting smaller at each recursive call, and the starting coin argument is either getting smaller or staying the same. So instead of going from the top down, starting at 200, 200, we could build from the bottom up. Let's start by initializing a solutions table, similar to our cache table. Next, since we'll be generating cache keys in a few different places, we'll write a quick helper function to produce the cache key for a pair of arguments. Our initial condition is that for each coin x, the solution count at 0, x is 1. That is, regardless of what the last coin we used was, if the amount left is 0, we have one way to meet that condition, which is to do absolutely nothing at all. Now we iterate for each possible amount left from 0 up to 200. Inside that loop, we iterate over the starting coins and ending coins, where the ending coin must be smaller than or equal to the starting coin. I haven't drawn attention to this yet since we haven't really needed it until now, but in Lua, the usual way to iterate over a table with integer indices is with I-pairs, and I-pairs produces two values at each iteration, the index and the value. Up to this point, we haven't needed the index, so I've just been calling it underscore. But now we use the index to make our iteration more efficient and skip over the invalid coin combinations. Inside of our nested loop, we note that if there are m ways to get to I pence left, with our last coin being end coin, then we should add those end solutions to the scenarios where we have I plus end coins pence left, and start coin was our last coin. This effectively goes back in time one step, iterating in reverse order from our previous recursion. We suffix our table accesses with or 0. In Lua, similar to JavaScript, if we try to access a value in a table but the key doesn't exist in that table, we get a default value, undefined in JavaScript or nil in Lua. However, nil can't participate in arithmetic, so if we get nil in either of these table accesses, we want to treat it as 0. Fortunately, nil is a falsy value, so it behaves well with respect to Boolean logical operators. Once we've done all of that, we print out the value at the top of our table, corresponding to our starting conditions. If you find this approach confusing, let's take a look at it another way. Let's draw out the table we've been building as a 2D grid. The x-axis is the coin denomination we used last, one of 1, 2, 5, 10, 20, 50, 100, or 200. The y-axis is the amount of money left. And we know that the top row, corresponding to an amount left of 0, is filled with all 1s, because in that case, we've definitely found a solution. In our first two recursive solutions we wrote, the naive solution and the cache-based one, we start at the bottom right corner at position 200, 200. Our recursive calls move up and to the left until we either arrive at the top row of known values, or fling ourselves haphazardly off the end of the table and overcount. In our most recent solution, we do just the opposite. We start at the top row, full of the known values 1, and slowly build down a solution from previous data, until we get to the bottom right corner and print it out. This is the same inversion of control we did way back in problem number 18, before converting our program into, a GNU makefile. So now we've seen several ways to solve this problem in Lua. Naively, using caching, and using a bottom-up dynamic programming approach. Since the target value of 200 pence is so small, we won't really need to do anything fancy with caching, so we'll focus on the naive solution going forward. This is our target program, and today we'll be writing it in our first ML dialect, specifically Standard ML. The original ML, short for meta language, first appeared in the 1970s, developed by Robin Milner. Since then, the language has evolved and branched off in a similar fashion to Lisp, creating several derivatives that vary in how similar they are to the original. The most well-known ML derivatives in use today, though certainly not the only ML derivatives in existence, are Standard ML, OCaml, and F#. Standard ML is a relatively minimalistic functional language, which is seen frequently in academia and is arguably the truest to the original Milner vision of ML, but with a formal specification to back it. OCaml, originally short for Objective Camel, is a natural extension of ML, which adds first-class modules, an object orientation system based on structural records, and a lot of quality-of-life syntax and semantic features. F# is an ML dialect whose primary goal originally was compatibility with the .NET ecosystem, which includes C# and Visual Basic, though modern F# can also compile to JavaScript and CUDA-accelerated GPU software. F#, being a .NET language originally, comes with an object orientation system heavily inspired by C#. The ML family also set the stage for pretty much every statically typed functional programming language in some way or another. Haskell and its derivatives such as Elm and Frege are influenced heavily by ML. Most theorem provers are either indirectly or directly inspired by the principles set forth in ML. Coq is written in OCaml, and although Agda's syntax looks more like Haskell, Agda's module system is straight out of ML. For today, we'll be focusing on standard ML, which will give us a firm foundation in a lot of the principles central to this family of language, for when we undoubtedly come back to them later. Standard ML was first standardized in 1983 and received one major revision in 97, appropriately referred to as Standard ML 97. Since then, the language has been mostly feature frozen, serving as a strong, consistent base for educational purposes and compiler experimentation. Standard ML is a mostly pure functional programming language. With a couple of exceptions that we'll discuss, all values are immutable. Standard ML doesn't track side effects like Haskell, so we won't be messing with an I/O monad or anything today. Basic declarations at the top level are written with val. Val binds a global name to a value. Remember that this is a functional language, so these bindings won't change later. Functions can be constructed anonymously with the fn keyword. For instance, this line defines a function called isPositive, which takes a single integer argument and returns true if its argument is greater than 0. We could define all of our functions this way, but that would get old fast. So we can also use the fun keyword to define top-level functions. In addition to being more convenient and readable, this syntax is also necessary for recursive functions. A val declaration can't refer to itself since it doesn't exist at the time it's being evaluated, but a fun body can refer to the function being currently defined. For example, here's a quick and dirty recursive factorial function in standard ML. This would be much more difficult to write without the fun keyword. You'd have to resort to something called the Y combinator, or fix function as Haskell calls it. Standard ML is statically typed, but you'll notice we haven't written any type annotations yet. One of the hallmarks of ML dialects is very powerful type inference. The standard ML engine infers that our factorial function takes an integer and produces an integer. We could have annotated our argument and return type explicitly, but in standard ML, we don't have to. Standard ML defines two numerical data types, int and real, which work exactly how you would think. Int represents integer values, specifically 32-bit signed integers, and real represents floating point values. The basic arithmetic operators, such as plus, minus, and times, are overloaded to work on integers or reals, but mixed arithmetic is not permitted. To add a real to an int or vice versa, an explicit conversion of one of the arguments must be performed. Division, on the other hand, is not overloaded. The / always represents floating point division and cannot be used on integer values, while the infix operator div performs integer division. Characters are represented using the char type, and character literals use a slightly verbose syntax starting with a hash sign. In practice, I don't actually mind that too much, as you don't tend to work with individual character literals in high-level languages like ML very often. Strings are simply defined as vectors of characters, though for convenience, ML gives us a type alias called string, which is defined to be a vector of characters. Lists, like in Haskell and Prolog, are forward-linked. A list is defined to either be the empty list or the cons of a value onto a tail list. Like in most statically typed languages, lists are homogeneous. That is, every element must have the same type. Note that most ML dialects use colons in the opposite way as Haskell. In Haskell, the double colon indicates a type annotation and single colon is the list cons operator. In most ML dialects, the single colon is a type annotation and the double colon is the cons operator. By the way, ML dialects write polymorphic types in the opposite order than you might be used to. Consider the type of a list of integers. In Java, we would write the word list, followed by angle brackets containing the word integer. C++, C#, and most languages in that syntax family use some variant of the angle bracket syntax. Haskell and most theorem provers use the same syntax for function application as for type application. So for most types, we would write list int simply juxtaposed together, though Haskell in particular has a specialized bracket syntax for lists. ML dialects, including standard ML, write the container type in postfix notation, so a list of integers would be written int list and read as integer list. This can trip up a lot of folks new to the ML ecosystem. In terms of random access containers, standard ML provides a vector type for immutable data and an array type for arrays whose value can change. These types are each defined within their own structures called vector and array respectively, alongside helper functions for each type. Note that while standard ML has specialized syntax for its linked list type, there's no special syntactic constructs for arrays or vectors. One point of note is that standard ML doesn't have an equivalent to Haskell's type class system. Whereas Haskell defines a single functor type class, for example, which gives us a very powerful generic fmap function, standard ML defines separate map functions for each container type in their respective structures. We'll see a lot more about structures later, but for now, when I say structure in ML, you can think of it as being sort of like a Python module. Standard ML gives us several options for building up composite data: tuples, records, and full-on named composite data types. Tuples are simple ordered products of values. We write tuple values using the same syntax as Haskell. That is, we write tuple values enclosed in parentheses with the individual elements separated by commas. However, tuple types are written using an infix star, just like multiplication. For instance, this is a 2-tuple containing the number 10 and the string hello. Its type is int times string. That is, its type is the product type of integers and strings. It's worth noting that, although the tuple type constructor looks like a binary operator, it actually takes any number of arguments. This is a tuple containing 3 integers. The star, used in type context, is neither left nor right associative. If we put parentheses on the left explicitly, we get a 2-tuple whose first element is itself a 2-tuple. If we put the parentheses on the right, we get a 2-tuple whose second element is a 2-tuple. But with no parentheses, we get a single 3-tuple which isn't nested at all. All 3 of these types are isomorphic in the sense that they contain the same data, but they are not the same. Like in Haskell, there's no 1-tuple type, since a single value tuple is isomorphic to its element type. The 0-tuple, which is often used as the result type of functions that are simply called for their side effects, is called unit, and its sole value is written as a pair of empty parentheses. Now is a good time to briefly touch on the calling convention of standard ML and other ML dialects. Like Haskell, the ML family of languages defines a function as taking a single argument and producing a single result. Formally speaking, functions of several arguments don't exist. This leaves us with 2 options: tupling or currying. With the first approach, we pack several parameters into one tuple and pass that as a single argument to our desired function. Suppose we want to write a function that takes an x value and a y value and returns the magnitude of the corresponding vector in the 2D plane. Using the tupling approach, we might write this. To be clear, this is not a function of 2 arguments. There's no such thing as a function of 2 arguments in ML. This is a function that takes a 2-tuple as its sole argument, and we immediately destructure that tuple using pattern matching. Currying, on the other hand, involves writing a function which itself returns another function taking the next argument, and so on until we've taken all of the arguments we care to take. We could write the same magnitude function using currying like so. Here, the magnitude function takes one argument called x, and then returns a brand new function which takes a second argument called y. That second function has access to both arguments and returns the real numbered result. In a type signature, the arrow operator associates to the right, so this type signature is equivalent to this one. Since currying is so common in ML, all of the common ML-derived languages provide syntax sugar for it, so we could have written our magnitude function like so. This is exactly equivalent to the explicitly curried version. Languages in the ML family differ in how they prefer to take arguments. OCaml, like Haskell, prefers the currying approach everywhere, unless there's a good reason to take a tuple. F# likewise prefers currying in most places, but uses tupling when interoperating with other .NET languages like C#. By contrast, standard ML generally prefers the tupling approach, except for higher order functions, which are often partially applied. So for example, the function textio.output has type outstring times string maps to unit. Specifically, it takes a 2-tuple as its argument, indicating both the target output stream and the string to write to it. On the other hand, list.map has this type. This is a higher order function, which means it takes another function as one of its arguments. In particular, this one takes a function and a list as its arguments. It's relatively common to partially apply higher order functions like this. The name list.map on its own takes 2 arguments, but we could also write something like this. This is now a function that takes the square root of every element in a list. We can store this function in a variable, save it for later, and call it whenever we want. If list.map had been written using the tupling approach to argument handling, partial application would take a bit more effort. In either style of argument grouping, a function of 0 arguments, which is simply intended to perform some side effect or query some value from the environment, is written as a function whose sole argument is of type unit. Note that we don't have to do this in a non-strict language like Haskell, since the side effect itself is tracked by the result type, usually the IO monad. But in ML, with strict semantics and no IO monad, we need to explicitly track when an effectful function runs. You can access the fields of a tuple directly by preceding the name of the tuple with a hash sign and then a number, indicating the one indexed position of the desired field. Note that this hash sign syntax is not a function and cannot be directly passed around to a higher order function like list.map. It's a special syntax that must be immediately applied to a tuple, even though it kind of looks like function application. It's also, according to most standard ML instructors, extremely weird. Most of the style guides I've seen recommend against this syntax, and instead prefer to use the much cleaner pattern-matching syntax to destructure tuples. Tuples are nice for ordered sequences when the individual fields don't need names, but standard ML also gives us a more powerful construction called records. A record is an unordered collection of named fields with known types. Note that the record itself doesn't need a name. This is a valid record type consisting of 3 real numbers, named x, y, and z. We can construct it like so. The fields in a record are unordered, so even if we add, for example, put y before x, we would still get a value of the same record type. Just like tuples, records give us 2 ways to access their elements. The more common way is with pattern matching. We can match against all fields in a record or a subset of them using an ellipsis to indicate our intent to discard the rest. If the name of a field is the same as the name of a local variable we want to assign it to, we can omit the equal sign entirely. We can also use the hash sign syntax with the name of a record field to extract a single field from records, though this syntax is discouraged for the same reason it was with tuples. In fact, tuples are really just records in disguise. The tuple type int times string from earlier is exactly equivalent to a record type whose field names are the numbers 1 and 2. Records and tuples work well enough for simple products of data, but the general purpose solution for representing complex data in standard ML is a data type declaration. Data type declarations can declare multiple variants, all of them named, and support self-reference, allowing us to define recursive sum of product types. Some of the best and simplest examples of this syntax can be found in the ubiquitous basis library. Here's how the basis library defines the option type. First, the type is polymorphic, taking a single type parameter called a as argument. Remember that type arguments are written before the type they're being applied to in ML syntax. An option is either a none, which takes no value arguments, or a sum, which takes an argument of type a. The value none can be referred to directly, and to construct a value of the sum variant, we apply the name sum as a function. Basis defines the type of lists similarly. Note that the name a-list that we're defining, in addition to being on the left-hand side of the equal sign, also appears on the right-hand side as a part of a constructor. This isn't a problem. A data type can contain another instance of itself in one or more of its variants. Note also that the constructor for the non-empty list variant is a binary operator, so to call it, we would write the operator in infix form. This covers the basics of standard ML's type system, but believe it or not, I haven't even gotten to the feature that, in my opinion, makes the ML family stand out most from the crowd. Its module system. We're actually not going to get into that right now because I want to get back to the Project Euler problem, but for those of you who are interested, I'll be posting a second video on standard ML where I take a deeper dive into what I think are the most interesting parts of an ML dialect, such as its module system. But for now, let's talk about Project Euler problem number 31. As a reminder, we were counting the number of ways to sum up to 200 pence using only denominations currently in circulation in the United Kingdom. This was our first solution, which didn't involve caching or dynamic programming and simply calculated the result recursively. Let's write it in standard ML. First, we declare our list of coin denominations, in order. Next, we write the count2 function. In following with the standard ML convention, we'll default to the tupling argument style here, so our function takes a tuple of 2 arguments, both of them integers. Next, we write our base cases. If the amount of money we have left to sum to is less than 0, then we overcount it and should return 0, indicating a lack of solutions on this branch. If the amount of money left is equal to 0, then we found a single solution, so we return 1. Finally, in our recursive case, we want to try every coin less than or equal to our starting denomination, and sum up the number of solutions we get with each coin. In Lua, we did this with a for loop and conditional, but in standard ML, we'll do it in a more functional style, using higher order list combinators. Start with the list of coin denominations. Filter it down to only the coins valid at this particular point in our recursion. Apply the recursive call to each element using list.map. Finally, sum the resulting list using a left fold with 0 as the identity element. Outside of our recursive function, we make a declaration that doesn't actually declare anything. The top level of standard ML only allows declarations, so making a declaration like this allows us to write an expression that will run, in our case a call to the print function, without binding the result to any name. Think of it as a main function, but instead of defining a function to do the work, we just do the work and then ignore the result explicitly. In our main block of code, we call the counter function, convert the integer result to a string, and print it to the console. This runs instantaneously and solves Project Euler problem number 31 in standard ML. But like I said, I haven't even touched on what is, in my opinion, the most important and unique feature of ML dialects. I'll be publishing a companion video to this one which goes into more detail on ML's incredibly powerful module system, so keep an eye out for that in a few weeks. After that, we'll be back with our normally scheduled programming with Project Euler problem number 32 in COBOL, a very old imperative programming language still frequently seen in business and finance systems. See you guys then.